And next up, we have Ismael from Lagrange Labs, who will be speaking about enabling trust minimize interoperability with non-interactive cross-chain state proofs.
I could have made that title a little shorter. In retrospect, I probably will next time. So, good afternoon, everyone. My name is Ismael. I am the founder of Lagrange Labs. So we build infrastructure to increase the expressivity of how on-chain data can be used in applications. So we oftentimes think about the expressivity of a state machine in terms of the execution environment. And when we think about increasing the expressivity of execution, we typically think about supporting new VMs, new opcode or bytecode sets, and allowing developers to interact with on-chain state through more ergonomic and easy-to-use languages than Solidity. But what we don't often think about is how state itself constrains the types of applications that can be built using a state machine. So I'm going to start with a very non-controversial statement, hopefully, that state machines require state. And what is on-chain state broadly? We can think of on-chain state as the current value of all variables and all data in all contracts on a given chain, in addition to all transactions, all events, all receipts at a given point in time. And as every block is inextricably linked to the previous block, you can think of a block header as a commitment to a version database with discrete updates that have occurred from genesis through the current state. And when we think about cross-chain state access in the monolithic or the single-chain context, we typically think about accessing state in somewhat easy-to-use, predefined function calls. So how do you get state on a monolithic chain? Typically, you would be able to interact with all variables in your contract. You'd be able to access some storage in the storage root of the chain if you wanted to run an MPT proof manually. And you'd be able to access it through cross-application view functions. And when we think about this in the cross-chain context, things get a little bit more dynamic and a little bit more complicated. So generally, you'll have different execution environments. You'll have different storage trees, receipt trees, and transaction trees. And you'll have cross-application states that span a series of different execution environments where access is fundamentally asynchronous. And so what this leaves us with, and this is how you can really think about state in the blockchain world today, is a data lake, a morass of asynchronously updated, different data structures that you are more or less unable to verifiably search, compute, or include the data from within your application. So at the point of execution, let's say of your contract on Solidity, you really don't have access to the same expressive types of computation that you would otherwise do in the Web 2 context, right? You can't query over on-chain state in SQL. You can't query multi-chain state and merge data in SQL. So you might say, well, what about storage proofs? I hear a lot of people at EthCC talking about storage proofs this year, and there are. But storage proofs are only a partial solution to this problem. Storage proofs allow you to say, at this point in time, in this memory slot, in this contract, there is this data. There is this value, these bytes. And while this is valuable, it is constrained in what it can show you. And with the computational overhead to access this data, you have to be very specific on what you're accessing. This is not a general purpose tool for querying over data. And so here's a thought experiment for everyone. Assume that you have a new contract. You have a contract on Ethereum. And this contract needs to access NFT-level application data from a different, let's say, the Pudgy Penguins NFT contract. And so you want to find all owners of an NFT, or sorry, all NFTs owned by someone with a pre-specified address. So how would you define this query off-chain? Very simply, you would just say, if it's on your database, select all from Pudgy Penguins contract where owner equals XYZ. You can think of an oracle, maybe if you were to index all this data off-chain yourself and then feed it back on and trust the oracle, you could do this too. But how would I do this on-chain? If my contract wants to trustlessly access this information from the Pudgy Penguins contract. Well, the answer is you'd have to run a loop on-chain through every single index of that mapping to figure out what every contract, what every NFT was in the index and the mapping, and then check who the owner was. Because it's a mapping on-chain, so it's a key value store, and the key is index and the value is owner. And so you can't query or index or search by the owner. And this is the case for most on-chain data. So you can't figure out how many users own USDC balances greater than X without going through every single index of all USDC balance owners. And so when you're thinking about on-chain state and on-chain data, there are certain questions you can ask. So who owns NFT X at contract Y? What is the price of ETH to USD on UniV3 at block N? But there are expressive and data-rich questions that you can't ask. You can't say, what are all the properties, what are all the NFTs owned by address X with property Y? What is the price of ETH to USDC on UniV3 over the past N blocks when factoring out outliers? Or you can't say, what is the standard deviation of price across this asset pair on this chain? And what is that over the last N blocks so I can derive volatility? You're fundamentally constrained by your access to data and the computation you can run on top of it. Now, this is where what we do comes in. What we allow you to do with our novel proof construction, called zk-MapReduce, is to compute over on-chain data in the single chain or the multi-chain context as if it was in your data lake. You can run MapReduce, Spark, RDD, and SQL on-chain state and prove the result to your contract with zero knowledge. Now, you might say, well, what is the security assumptions of the data? Because if the data is bad, the computation doesn't really prove anything. So this can be thought of as a transport layer agnostic proving system. So what this means is the block header that's used as the input to this proof can come from anywhere. If you're on Ethereum and you have access to block.header in your contract, you can just use that. So it's no security guarantees beyond the execution environment. If you are on an L2 and you can get the L1 state read from the canonical bridge, use that. If you're somewhere else and you want to opt into Layer 0 or Axelar or Polymer or one of the many cross-chain solutions, you can use their state root and their block header. And you can verify these proofs with respect to a predefined point of trust that you've established in an existing cross-chain protocol. It's not our job to tell you what state to trust. That's the job of the application developer. What we do is we allow you to establish that point of trust and now have more expressive and dynamic and data-rich computation sitting on top of it. And so what's required for a proof? Well, a block header, the thing we've been talking about for the last few minutes. Then a specific range of block numbers that can be proven with respect to that block header. And then a series of storage slots that are going to be used as part of this computation. Next, you specify the computation, and then there must be a contract in the destination chain to verify this computation that we deploy. So very simple, doesn't require much, and drastically improves the surface area of applications you can build. Now, what this does at a very high level is allow you to compute across on-chain state like a data lake at a high cardinality of depth of historical data and a high width with respect to the amount of data you want to compute per proof. And so here's some use cases real quick on these. I don't want to bore everyone, but we've talked about the GameFi application before where you want to search over data to figure out which NFTs are owned by someone. Obviously, that's a perfect example of the type of thing you can now compute with this. You can think about a DAO use case. You're on an L2, and you want to figure out who has engaged in some activity with your contracts to reward them. Differential fees on trading, maybe. Or, for example, figuring out who has voted on your proposals to give them more voting weight in the next one. And next, we can talk about the more interesting DeFi ones, right? Volatility, something that you'll need for Black-Scholes or options pricing, right? You think of, I can get a volatility oracle, but are you trusting the oracle? Are you trusting the data provider? If that goes down, it can potentially compromise hundreds of millions of dollars of assets that your protocol holds. What's the simpler solution, the more secure solution? You specify the computation to derive volatility over the time frame you want, at which point you can then verify the result of that on-chain whenever you need it. And so you might say, well, everyone says zero-knowledge proofs take forever to compute. Why does this giant proof that we're obviously computing not take forever? And this has to do with some interesting properties of our proof construction that make it far more performant at scale. And the property that our proofs have that proofs before us don't have is something called updatability. You can take a proof on overlapping or non-overlapping data, and you can compute over that. And you can derive some proof of some computation, and then you can take a chunk of that proof that you pre-computed for another use case, and you can include that in another proof. And what this allows us to do is to drastically reduce proving time to minimize the latency that is required for these large dynamic proofs. And this allows us to scale proof computation through composition, not recomputation. So if you guys want to learn more, we'll be presenting the paper at Stanford Blockchain this year, or our research team will be. And around that time, we'll be releasing the paper as well as a test net of our construction, the overall proving system, and some of our early use cases. So thank you, everybody. Any questions?